Good morning, everyone. So this is our last lecture for Module 1. And after this, your Module 1 exam will open in zip grade. You'll have 24 hours to do that. Please take it slow, make sure you understand the questions, submit at the end. I will have the keys uploaded tomorrow, and you'll be able to see your scores sometime tomorrow after 3 p.m. or so. And then tomorrow as well, I'll open up Module 2 in Canvas. So I think we have 7 lectures for that maybe. So same format, you'll see all the lecture notes put in there the day of the lecture. And there's 2 exams, 2A and 2B for that. The first one is on mass spec and IR, and then the second one is on NMR. So make sure you have those dates set in your calendars. Again, they're listed in the syllabus. And then finally, if you haven't done so already, please download the Excel file to track your points so that you know how you're performing. Any questions before we get into it? So up until this point, we were talking about hydrocarbon functional groups. So alkanes, alkenes, and alkynes. Then we looked at atomic orbitals versus hybrid orbitals and how they can account for the different bonding patterns seen in alkanes, alkenes, and alkynes. So that was sp3, sp2, and sp hybrid orbitals. And so now we're going to move into the other functional groups that contain heteroatoms. So up until this point, everything was either a carbon-carbon or a carbon-hydrogen bond. Now we're going to move across the period 2 from carbon. Then we're going to look at putting nitrogen in, then oxygen, then halogens. What are their bonding patterns? What are their names? And where we're going with this is basically we're learning the relationship between the word and what needs to be present in terms of the specific bonding arrangement to make that functional group. And then Module 2 is how do we use data to know if that functional group is actually there or not. So again, so far you've seen alkanes, alkenes, and alkynes. So that functional group name is telling you a little bit about the bonding pattern. So when we start putting nitrogen into a molecular formula, the functional groups are listed on this page. And I'm going to give myself some wiggle room here. These are not all of the nitrogen containing functional groups, but the main ones that we'll deal with. So the first ones are amines. So amines, and we can think of those as derivatives of ammonia. So we know ammonia is NH3. And really what we're going to do is take one of those hydrogens and substitute it for carbon. And then there's different classes of amines. So shown to the left here is a primary amine. So when you see the 1 in that degree sign, we would say that's primary. And the way that amines are classified, and let me just throw this out there, these classification systems can be different for different functional groups. So we have to know what kind of heteroatom is involved. So a primary amine has an NH2 group, and the nitrogen is attached to only 1 carbon. So there's 1 carbon. Say we take ammonia and we do 2 substitutions for carbon. So that's now a secondary amine. So we have 1, 2 carbons. Now sort of the Rubicon here is right here. A tertiary amine has 1, 2, 3 carbons. And the main difference between primary and secondary, those both have an NH bond. A tertiary amine does not. That will become important when we start learning about these spectroscopic methods in Module 2. And then finally, we can have a quaternary amine. Notice there's no H that we can substitute. So what is happening is we know that nitrogen will form 3 bonds and it always has a lone pair. That lone pair actually gets occupied for the 4th carbon. So 1, 2, 3, and 4. Notice the difference now. There's this plus charge, and we're going to talk about that today as well. That's called a formal charge. How do we know that it's plus? How do we know when it could be minus? What is the deviation from the normal bonding pattern? So again, nitrogen has 3 bonds and a lone pair. That gives it the octet. This now has 4 bonds, so it's not the normal pattern, so we have to account for that with a formal charge. So here are the amine classification systems based on the number of attached carbons. So you really have to pay attention to the letters, the vowels, the consonants. So amines begin with A. A nitrogen-containing functional group that has a pi bond is called an imine. That begins with an I. So amines have a carbon-nitrogen pi bond. So notice the nitrogen is still in the neutral pattern. We see 3 bonds. It has a lone pair, which I'm drawing in now. But we need to assume that it's there. So three bonds in a lone pair. And again, remember we learned about single, double, and triple bonds. As long as the element is obeying its sort of normal bonding pattern, that's when it's going to be neutral. When these charges start to show up is when they don't have that pattern. So a CN pi bond, that's called an imine. So the next one is an enamine, and that's it's the word portmanteau or something when you jam 2 words together and make a new one. An enamine is an alkene and an amine. So we can see the alkene, that's the carbon-carbon pi bond, and directly attached to one of those sp2 hybridized carbons is an amine. So that's called an enamine. So moving up to the next one where the nitrogen is sp hybridized. So we have sp hybridized carbon, sp hybridized nitrogen. There's a triple bond. So overall, there's 2 degrees of unsaturation. That's called a nitrile.
Can you describe the difference between amine and enamine?
So maybe I'll do it in some color here. An amine has a carbon-nitrogen pi bond, so that's shown in red. an enamine has a carbon-carbon pi bond. I'll show that in blue. So again, the word or definition for functional group is the specific bonding pattern. So you need those minimum number of elements present to make it that functional group. So for a nitrile, you have to have a carbon triple bonded to a nitrogen. This thing over here, these two carbons, that can be anything. But this part of it right here is referred to as a nitrile. Yep.
About the enamine, is there any specific criteria when you talk about the degree of unsaturation of nitrogen in it? Is it compulsory to be 3, can be 2, or 1?
So I guess when I'm classifying like degrees of unsaturation, I'm talking about like the minimum amount of stuff you need to make an enamine is a carbon-carbon double bond and then a nitrogen directly attached to it. So those 3 atoms right there. This other stuff hanging off can be whatever. So just like with hydrocarbons, we saw that we can make rings out of those. They're called cyclic alkanes or cyclic alkenes. If you shove a nitrogen into a ring, that makes a heterocycle. And again, hetero just means different. That's these other elements besides carbon and hydrogen. So the degree of unsaturation here is coming from the ring itself. Notice as these structures are drawn, every atom is sp3 hybridized. So we have a 3-membered ring, 4, 5, and 6. I mean, you can go on beyond that. As we learn more reactions and reagents, these things will have common names. We can refer to them. By necessity, a heterocyclic compound with a nitrogen, the nitrogen has to be secondary minimally because you can see there's 1, 2 carbons you need to constrain it in the ring. The H, you could substitute that for another carbon and then it would be a tertiary heterocycle. So I've listed these as aromatic. Aromatic compounds, by definition, are heterocycles. So they have to be a ring. And then within that ring, you have pi bonds. So this 5-membered ring is called pyrrole. And the 6-membered ring is called pyridine. So as we progress through the semester, we'll talk about these nitrogens. I mean, it's written as a blue N. We recognize they're both nitrogens. You can count the bonding pattern. So each of them are showing 3 bonds. They have a lone pair of electrons. But these nitrogens have very different reactivity when they're embedded in these rings. So as you're drawing things, always think about lone pairs that are on heteroatoms. What orbitals are the lone pair of electrons in? So just like you can classify carbon hybridization, you can also do that for heteroatoms. Any questions? So again, pay attention to the names: amine, imine, enamine, nitrile, heterocycles, aromatics. So this molecule gifrotoxin, we talked a little bit about carbon hybridization, counting carbons, that sort of thing. If we look at the nitrogen atom, how would you classify the nitrogen? So this one will be tertiary. So walking out from the N atom, we hit a carbon, that's one, second one, and a third one, so that's tertiary. So that's a taste of nitrogen functional groups. Again, that's not all of them. As we move across the periodic table, the next thing we hit is oxygen, and there's more of these for sure. And I would say this is a pretty important slide because it impacts Module 2 quite a bit. Basically, how do we know that there is nitrogen or oxygen or a halogen in a molecular formula? And there's a lot of oxygen-containing functional groups. So the first one we're going to look at are alcohols. And again, we can think of these as derivatives of water. We're going to take a hydrogen from water and substitute it for a carbon. So minimally, what you need for an alcohol is an OH group. So when I say alcohol, you should think OH. Now, alcohols are classified in a different way than amines are. So in the first example, we see the OH group here. So they always have to have OH. So let's move away from the oxygen to that carbon. That carbon has a name. It's called the carbinol carbon. And the alcohols are classified from that carbon. So you're standing on that carbon, and then how many carbons are attached to it? So the carbinol carbon I have in red. How many carbons are attached to it? There's one. So that's a primary alcohol. In the middle example, there's the red carbon that we need to analyze or classify from. And then we can highlight in blue, there's 1, 2 carbons, so that's secondary. And then finally, the last example has 3 carbons. So that's tertiary. So remember that amines could be quaternary, where the nitrogen has 4 carbon substituents, then the formal charge. You cannot have a quaternary alcohol. And again, because the bonding pattern, you have to have an OH that has to be attached to carbon. If carbon has 4 bonds, one of them is taken by OH. So the maximum number of other carbons is 3. So say you take water and then you substitute both hydrogens for carbon. That makes an ether. So here's our oxygen. Moving out from that, we have a carbon and a carbon. In that case, that's called an ether. As we get through these functional groups, we're going to have a summary slide on how do the bonding arrangements impact the physical properties. So from an alcohol to an ether, since you're substituting that H with another carbon, ethers in general will have lower boiling points than alcohols. And the reason for that is alcohols can hydrogen bond. So that's a non-covalent interaction that affects the physical properties. When you remove that, it impacts the melting and boiling points quite drastically.
Which one can hydrogen bond?
The alcohols. So those two examples have a carbon-oxygen sigma bond. The next couple examples, we're going to make a carbon-oxygen pi bond. So a pi bond is a degree of unsaturation. We've seen that already with a carbon-carbon pi bond and an alkene. When we have a carbon-oxygen pi bond, just the CO double bond is called a carbonyl group. So there's a lot of these because we're showing two bonds to carbon. That means it has two other bonds we can make. And so depending on what is bonded to that carbon will change the functional group name. So the first one is called an aldehyde. We can see the CO double bond. Aldehydes have an H and a carbon. So by necessity, in an aldehyde, the carbonyl group has to be at the end of the carbon chain because of that H group. If we move that carbonyl to an internal carbon, that makes a ketone. So the carbonyl carbon is now bonded to two other carbons.
So the carbonyl is just a single bond between oxygen and carbon?
Yeah, again, that's where the vowels and the pronunciation are important. So again, carbinol, that's carbon-oxygen sigma bond. And then carbonyl, that's your pi bond. The next sort of group of them are called acid derivatives. A common thing amongst all of them when you spot the pi bond, on one side there's a carbon. Then on the other side is a heteroatom. They're called acid derivatives because they can all be made from carboxylic acids. So a carboxylic acid now has your carbon on one side and then an OH on the other. So that collection of elements is known as a carboxylic acid. You cannot divide it any more than that. So if you call it some sort of ketone alcohol, that is incorrect. Again, notice the bonding pattern. An alcohol has an OH group. An acid also has an OH group. But in the acid, that carbon is sp2 hybridized, and then it's located in a carbonyl CO double bond. Yeah.
So on that carboxylic acid, where you have the red dot of that carbon there, is that where the functional group begins at that carbon, or would it not be the carbon that is attached to the oxygen?
So I would say minimally, that's what you need to form a carboxylic acid. Then anything that I didn't highlight can be like whatever. So from an acid, we can take the H and then substitute it for a carbon. That's called an ester. Notice the spelling. An ester is not an ether. So if we highlight what we need for an ester, we have the carbonyl, that oxygen, and then some other carbon. So that's the minimum stuff that you need to form an ester. So if you put your eyeball right at this central oxygen here, and then you move out from that, you see that oxygen is bonded to two carbonyl groups. That's called an anhydride. So an means without, hydride means water, so that's without water. So anhydrides arise from the condensation of two carboxylic acids with one another. And then the last example is called an acid chloride, but in reality, that could be any halogen. So fluorine, chlorine, bromine, or iodine. Acid chlorides just tend to be the most common. So you have a carbonyl and then a bond to a halogen.
So it doesn't have to be chloride, just any halogen?
Correct. So what if we put nitrogen on one side? So notice the name of these now. These make amides. So you have a carbonyl group that's then bonded to a nitrogen. That's called an amide, and then you can classify amides the same way you do amines. If we look at the nitrogen, we can see it's bonded to one carbon, so that would be a primary amide. We start substituting off the H's for carbon, so now we have secondary and then tertiary. So in terms of the bonding pattern, what you're looking for, the carbonyl group, that's then bonded to a nitrogen. And the nitrogen is what you classify it as primary, secondary, or tertiary. So oxygen heterocycles, we shove an oxygen into the ring. So they're heterocyclic, but what other term could we use to describe their functionality? They're definitely rings, but one of the other terms we already used on this slide.
Ether.
So they're ethers. So the oxygen atom is bonded to 2 carbons. So these are all ethers. So there's different ring sizes. So you can have 3-membered ring ethers. Does anyone know a common name for that functional group? Huh? Epoxide or epoxy. So those are pretty common. If you look at a small ring, remember from geometry, what do the angles of a triangle have to equal? And so you have 3 angles in there, so that, what's the angle of any sort of 3 atoms? 60. What's a normal sp3 hybridized carbon? What should its bond angle be? 109. So our normal carbon has a bond angle of 109. In here it's 60. So how does that translate? Who goes to the gym? Do your chest exercises? So here, if you have some dumbbells, you kind of feel some stuff. When you start bringing it together, you feel that squeeze in your pectoralis muscles. That's strain. So the same thing happens with carbon. When it deviates from that bond angle and gets strain into it, that means reactivity. So even though you're looking at a triangle, try to think about it in terms of the hybridization and orbitals and stuff like that. That will help you understand reactivity. 6-membered ring with oxygen is pretty common in nature. We'll talk about those in organic 2 when we look at carbohydrates, so glucose and derivatives like that.
Whatever the bigger than 6 is.
Yeah, you can go beyond. I'm just showing you sort of the more common ones. And then I've shown you one aromatic oxygen heterocycle. This one's called furan. And really for now, what you're looking for is just the bonding patterns to recognize these different functional groups. Any questions? It's like going to a family reunion and meeting, third cousins you never knew you had. It's a lot of stuff to remember, right? So looking at the alcohol group in gifratoxin, how would you classify this alcohol? So this one's primary. So we're standing on that carbon. We can see that it's only attached to one other carbon, so it's primary. And so why are we belaboring all of this in terms of the classification and stuff? When we start learning reactions, say there's a molecule that has 3 different types of alcohols in it. How do you know which one of those groups the reagents are going to act upon? Because an alcohol is an alcohol. If the reagent can act with any alcohol, how is it selective? And from the first sort of part of that is classifying it. Once you know how to do that, you can say, yes, this reagent only acts on secondary alcohols. So we marched through nitrogen, oxygen. We're at halogen ones now. And these are called alkyl halides. We know that halogens will have a sigma bond and then 3 lone pairs. And then these are classified the same way as alcohols. So the carbon bearing the halogen, how many carbons does it have? So primary, secondary, tertiary. And again, why is that important? When we start looking at mechanisms, a mechanism is how a reaction proceeds. How are the electrons moving to break bonds and make bonds? By classifying the halogen, it will tell you what type of mechanism can occur. So some mechanisms only go through primary, some only go through tertiary. And so by knowing that, you know which mechanism it's going to be, and then you can predict out what the product should be. And then we saw the acid chlorides on the oxygen slide. So we've seen the names, we've seen the bonding patterns. This is just a brief slide or two on how do those bonding patterns affect the physical properties. And the last couple columns here have these non-covalent interactions. Things that are kind of light yellow, those are pretty weak. The green ones are strong. So you'll notice that the compounds listed, so we have water, ethanol, ethanoic acid. Those are the rows with the green highlighted, hydrogen bond donor acceptor. So they have the strongest non-covalent interactions you can get. And look at their boiling points. So water boils at 100, ethanol 78, ethanoic acid 118. So the presence of those functional groups impacts the physical properties greatly. Because when you look at the lack of them, the boiling points are quite lower. So here's a temperature scale reference for you on the top here, absolute 0, that's Kelvin. Then the bottom here, that's Celsius. 0 and 100, that's our sort of milestones we use with water. The human body is 36. Room temp is about 25. And then below that, these arrows are to help you understand how to think about temperature. So starting from absolute 0, where there's no heat, you're adding heat, the arrow's red. So you're increasing in temperature. So solids will melt into liquids, liquids will boil into gases. Now, if you have a system with heat and you're removing it, you're going to use the cold arrow, the blue one. If you have a gas and you're cooling it, it will condense into a liquid. The liquid will then freeze into a solid. So let me just draw out what we mean by these two things that are in green here. Hydrogen bond donor and acceptor. We'll do water. Alcohols and acids both have OH groups, and then conceptually it's similar type of interaction. So there's our water molecule. Oxygen has 2 sigma bonds, 2 lone pairs. The geometry is bent because we're only considering the elements, not the lone pairs overall. So let me draw another water molecule. Let me first say that OH, so we recognize that as a sigma bond. It's a covalent bond. Covalent means there's sharing of those electrons. And furthermore, it's polar because there's a difference in electronegativity. So that's the normal bond you're used to seeing. What I'm going to draw now in blue is a hydrogen bond. So I'm going to draw a dashed line. So we're still using that word bond, but it's, again, not the normal sigma bond that you're used to seeing. It's an attractive force. So the lone pair from one oxygen is attracted to a hydrogen of another water molecule. And again, why is that? Because hydrogen's delta plus, the oxygen's delta minus, due to the difference in electronegativity. When we get into module 3 and we start talking about bond strength, what's the difference between a CC and a CH bond in terms of the strength? Those are kind of our benchmarks. Hydrogen bonds, since it's non-covalent, they're weaker. But in this table, they're still stronger than these dispersion and dipole-dipole interactions that we've seen in Gen Chem. So why does that affect the physical properties? I've just drawn 2 molecules, but imagine, each molecule of water is surrounded by many others. So there's a lot of these interactions. If you have liquid water and you're applying heat, you're not breaking any chemical bonds. You're not breaking OH bonds. You have to break that attraction, that hydrogen bond. So you have to put more energy in when that's present. And since you're doing that, the boiling points are typically higher. And again, you can draw sort of the same thing for ethanol or ethanoic acid, that sort of interaction. So what's a donor and what's an acceptor? So in terms of the hydrogen bond donor acceptor, so the thing with the OH, that's the donor. The thing with the lone pair is the acceptor. So an aldehyde oxygen has a lone pair. So it can only be an acceptor. It doesn't have an OH. So if you take, say one of these aldehydes, put some water in there, that lone pair can form a hydrogen bond to water. So the aldehyde is the acceptor, the water is the donor. And this sort of interaction can help explain, to a certain extent, why organic molecules can be soluble in water. So we know that O versus C, there's a difference in electronegativity, so that's a polarized covalent bond. We would say that's a polar functional group. We know from Gen Chem that like dissolves like, and then you could rationalize why, to some extent, you can get aldehydes soluble or miscible in water. Questions?
So in this instance, the water is still the donor, and that oxygen there is the acceptor?
Yes. So while that may seem boring or trivial, that whole concept of non-covalent interactions was really what fostered the race to figure out the structure of DNA. So that's kind of organic 2 stuff we'll talk about, but given these functional groups present in DNA, how are they arranged? And then what dictated that arrangement? A lot of it is based on hydrogen bonding, which we all know now because we can read in textbooks, but at the time, there were different proposals about what DNA actually was. The hydrogen bonding is very important kind of for the end of organic 2, and then if you go on to biochem, a lot of enzymatic reactions are dictated by hydrogen bonding. This is a lot of stuff. I don't expect you to digest it or know it for the exam. It's just a way of helping to see the trends of how functional groups change things. Let's look at the row highlighted in yellow here. So C1 just means 1 carbon. So a 1 carbon alkane, that's called methane. And then below here is the melting and boiling point. Imagine we take a hydrogen from that and we substitute it for something else. We then make new functional groups. So hydrogen to bromine, that makes bromomethane. And what you want to think about is when that substitution happens, how does that help explain the change in these physical properties? So we could also substitute for OH, that makes methanol. Make a pi bond, that makes an aldehyde, that's called formaldehyde. Or we can make an acid, that's called formic acid. You ever step in an ant pile? Start crawling on you and biting you. So typically fire ants, what you're feeling in that sting is formic acid. So that's kind of neat. They use that as a chemical defense. So the progression from left to right is just showing you the different functional groups. And then up and down, we're just adding carbons to the chain. The point of that is really when you're adding more carbons to something, it's not affecting the physical properties a whole lot. It's the nature of the functional groups involved. Questions? So we have two more things to get through. So we know visually that we can look at a structure, we can count the pi bonds and the rings. That will give us the total degrees of unsaturation. We also saw that when we're given a formula, we can use this CnH2n plus 2 to calculate that as well. But what about when we start putting in heteroatoms? What's the process then? If you're given the structure, you can still count the pi bonds and rings, but what if you're given the formula? What do these different heteroatoms do to the hydrogen count? That's what we have to figure out. So remember, we're always going to use that alkane formula, CnH2n plus 2, to figure out the maximum number of hydrogens for any n number of carbons. So as we move along the periodic table, N to O to halogen, they'll do different things to the existing hydrogen count. So whatever you're given, you have to modify. So anything in the nitrogen group will subtract one hydrogen for any number of those nitrogens or phosphorus or whatever. And this is something that if you look at enough structures of amines, you would be able to figure out how the amine formula differs from an alkane formula. Oxygens do nothing to the hydrogen count. Halogens have a similar bonding pattern to hydrogen, so they will add 1 for any number of halogens you see. So let's run through the logic here. Can you picture that molecule in your mind? Can you count the rings and pi bonds? So you no longer have the molecule in front of you, but now we're given the molecular formula. So we're going to do the same thing and figure out the degrees of unsaturation. The carbon count will never change. It's the hydrogen count that's going to change based on the heteroatoms. So remember we said oxygen does nothing, right? And then nitrogen will do what? So it's going to subtract 1. So H29 becomes H28. So you have to reduce it down to a CH formula. So our N is equal to 19. So we plug that in there, we get C19H40. So that's the maximum number of hydrogens for 19 carbons. And so then we just subtract out our modified one. So we get H12. Then a degree of unsaturation was defined as H2. So we get 6 degrees of unsaturation.
Can you explain why you select one?
So nitrogen's the one with the weird bonding pattern, right? Carbon has 4 bonds, nitrogen has 3, oxygen 2, halogens 1. So 4, 2, and 1, those are even. Because nitrogen's odd, it will affect that hydrogen count, so you have to subtract 1 out. So we would end up with D here.
Will we have to draw structures of something with heteroatoms in the exam? Will we able to?
So fortunately for you, all the exams are multiple choice, so you don't really have to draw too much. You'll have to look at molecular formulas, figure out degrees of unsaturation, and then based on that, could this, that, or the other be present? So you have to know when you're looking at, like, what does it mean to be an ester? What's the minimum stuff you need in there? And do the responses meet that criteria? So you might have to draw some things out to I think I've made the questions chat GPT proof, so that if you put the work in, you'll understand things, but if you put them into AI, you might not get the right answer. Not because I'm wrong, but because AI hasn't been trained yet. So here's another example. See if you can modify see if you can modify the given to see how the different heteroatoms affect the hydrogen count, and then ultimately what the degrees of unsaturation are. Missing a 3 here. So the modified should be C14H. What? H12. So if H9, we subtract off the nitrogen, that's H8, then we add 4 back in, so that gets us H12. So N is equal to 14. So that should be what, 28? No? 30? So that's the theory, or the max number of hydrogens. Jesus. So we should get 9 degrees of unsaturation. Questions?
So there are degrees of unsaturation. Does that mean that fully saturated, like, functional groups won't be present?
I guess that's probably a confusion of how things are stated. So remember, a degree of unsaturation is a pi bond or a ring.
Okay.
So when we say that, those things have to be embedded in a functional group. You can still have a saturated carbon, like an sp3 hybridized carbon, in a molecule. And then some other place there's like a pi bond or something, you know what I mean? So one thing you could do, after class is, go look up this molecule and then see if you can identify what those are. And then what, are they pi bonds, are they rings? And then from that, what are the names of those functional groups?
Why are there so many HIV models?
What?
HIV treatment models. It was the same with AGT. There's another one.
Yeah, there's a lot. So Dr. Kessel in the Chem and Biochem department studies HIV. So within HIV, there's a life cycle of how the virus replicates. I think there's like 6 stages. And there's probably like 3 to 5 drugs for each stage. So you're trying to basically block it at each thing. No one drug will kill it. That's the issue. Okay, so that's degrees of unsaturation with heteroatoms. And now we need to get to this thing about charge. When do we know to put a charge on an element? So visually, it comes down to you need to be able to recognize what is the neutral bonding pattern for those elements. Carbon, it's 4, nitrogen 3 plus a lone pair, oxygen 2 plus 2 lone pairs, halogen 1 plus 3 lone pairs. But remember, from those 4, 3, and 2, you can have single, double, triple. They can be different based on the hybridization. So if it's not the neutral or normal bonding pattern, we have to assign a charge. And I like to do it this way, using the group number. And so these were I keep wanting to call them Roman numerals, but they're not. We're going to use these group numbers in these calculations. So you take that group number minus the number of unpaired electrons minus 1/2 the bonding electrons. So this was that molecule AZT. And you'll notice in this collection of atoms here, that nitrogen's negative, that one's positive. Why is that? So if we focus on this nitrogen, visually you can tell it doesn't have 3 bonds and 1 lone pair. It has 2 bonds and 2 lone pairs. So it's not the normal pattern, so we have to calculate the charge. How do we end up with minus? So we have 5, and then we want to minus off here number of unpaired electrons, that's 4. And then we need to subtract off 2 times 2, that's another 4. So what about the other one? It's still nitrogen, so group 5. Unpaired electrons is 0. So we're showing 4 bonds, so that's 8. So that ends up being +1. I would encourage you to go along any other atom in this molecule and prove to yourself that they all have no charge. So you could do that nitrogen, or that oxygen, or that carbon. You plug it into there, the answer is going to be 0. So I said we didn't see all of the nitrogen-containing functional groups before. This is another one called nitro. So that's NO2, and it's represented here. So the blue nitrogen, the red oxygen. What charges should go on each? So nitrogen has 1, 2, 3, 4 bonds. It doesn't have a lone pair. Oxygen has 1 bond and 3 lone pairs. So the N should be what charge? So plus, you have to balance things off, therefore oxygen's minus.
Is it ever going to be plus or minus some number? Or like +2, -2?
I'm gonna say 99% of the time no. Just giving myself that 1% leeway. When you start seeing like higher order charges like that, it's for the molecule itself, not any one particular atom. In lieu of the time, I'm gonna let you guys do that one. So before we get to that last thing, in the middle of this table here is just summarizing what we've seen when we draw Lewis dot structures. Here's your elements, the number of bonds, number of lone pairs. So visually, when you're looking at things and it doesn't match that, you have to use the formal charge equation. And then these other 2 columns summarize what the bonding patterns will be for those elements when things are negative or things are positive. And I've thrown in some names here because the names do change a little bit. You can have negatively charged hydrogen, negatively charged carbon, that's called a carbon anion, so on and so forth. You can make positively charged elements. Those have different names. And why are these important? So typically in organic reactions, we form reactive intermediates, and they will have bonding patterns that are not neutral. So that's a skill you'll want to develop in either calculating it or just recognizing it as we proceed. thing. So I think we have time to do this one. Question mark, colon, less than, or B. I don't know why it looks like that, but which one's not correct? So that one is not correct. The second one is the neutral bonding pattern. The third one is when oxygen has 3 bonds, 1 lone pair, it's positive. The last one is 3 lone pairs, 1 bond, it's negative. Because I need to cover one more. So we got about 3.5 minutes here. And just like any good meal, there's always room for Jell-O. So we're going to squeeze it in here. The last thing is resonance. This is important because if you look at the molecule that you assign the plus and the minus on the N and the O, that nitrogen had 2 oxygens on it. And so the oxygens are not different, even though when we sort of draw them, they might look different in terms of sigma bonds and pi bonds. Resonance is the movement of electrons. So even though I'm showing you 2 structures on this slide, they're really the same molecule. They're called hybrids. See the negative charge on the right oxygen? And then over here, it's on the left oxygen. How does it get there? We can move that lone pair of electrons to form an oxygen-nitrogen pi bond. And then in doing so, since we're making a bond, we have to break a bond. So the pi bond electrons go onto that oxygen. You can still calculate the formal charge the same way. But what's the same? The nitrogen's still plus. That hasn't changed. All we've moved is the negative from here over to the other one. But these are not separate structures. What it's telling you is that each oxygen is kind of half negative. That in that region of space, they're sharing the lone pair of electrons. So resonance is when you can move a lone pair around, you can move a plus charge around, or an unpaired electron called a radical. So I know this is kind of a wham bam thing here. Let me just state that resonance is not the movement of atoms. So see this hydrogen here? If I move that up here, that's not resonance. Those are isomers. Resonance has to maintain the bonding pattern. All you're moving around is charges or electrons. So with that, we'll go ahead and end. There's some other practice stuff you can do on the remaining slides, but do your exam, submit it, and look for your scores tomorrow afternoon.